Saptarshi sir, shall we start, sir?
Hello.
Yes, sir.
Yes,
Shall we start, sir? Yes, sir.
yes, fine for me, as you wish.
Yes. Yes, sir.
Can you
Yes, sir.
hear me?
Yes, sir. Perfect, sir.
Perfect, perfect.
Yes.
So, yeah, means if you want to start, whenever you want to start, we can start.
I'll start now, sir. Formally, I would like to give a brief introduction, then we can start the session.
Okay.
Okay. So, very good evening. Ellargu Shubha Sanjay. I welcome all of you today on today's Talent Search Program webinar series. Today, we have with us Dr. Saptarishi Chaudhuri, sir, from Raman Research Institute. Before starting today's session, I would like to give a brief introduction about Dr. Saptarishi Chaudhuri, sir. He has obtained his PhD in experimental physics from Tata Institute of Fundamental Research (TIFR), Mumbai, for his work on ultra cold atoms and Bose-Einstein condensation, which is known as BEC. Thereafter, he worked as a postdoctoral researcher at École Normale Supérieure, Paris, France, working with ultra-cold fermionic atom mixtures and ultra-cold molecular physics. During his second postdoctoral research assignment at European Laboratory for Nonlinear Spectroscopy, University of Florence, Italy, he worked with interacting Bose-Einstein condensates in disordered potentials and particularly studied quantum localization. Afterwards, as a research fellow, senior postdoctoral researcher, Dr. Saptarshi led a building a new experimental facility at Center for Quantum Technologies, National University of Singapore, for trapping neutral lithium atoms in optical lattices. And he is currently an associate professor at Raman Research Institute and indigenously built a state-of-the-art experimental facility to study mass imbalanced ultra-cold atom mixtures for fundamental science as well as application-oriented research aimed towards building extremely sensitive quantum sensors using neutral atoms, in particular magnetometers. He received several awards recognitions for his research work, including a letter of appreciation from the Prime Minister of India. Apart from that, sir has published many publications in many national and international reputed journal papers. With this brief introduction, I welcome once again you, sir. Also, I welcome all the teachers and students who are with us today in this WebEx platform as well as in the YouTube channel. With this brief introduction, welcome you once again, sir. Before starting the session, I just want you to tell the names of the physics Nobel laureates also, sir, please. Thank you, sir.
Okay, so thank you very much for this wonderful introduction. I hope you can see my presentation
Yes,
on the
sir.
screen. Great. So, as you know that this year's Physics Nobel Prize has just been announced, I think 30 minutes back, maybe 1 hour back. And this Nobel Prize is given for the work, experimental work, on producing attosecond laser pulses and its interaction with electrons, and a subject which will be pretty closely related to the talk what I am going to give to you. At least the general ideas will be similar, and three very well-known scientists have been awarded for this effort, though the research related to lasers and laser matter interaction is being carried out all over the world by many scientists. So without getting into too much detail, I will start to introduce today's topic, which is uh, I will give this lecture on quantum mechanics and some of its modern application, because by now there are lots of application. And since I was asked to make this talk for specifically for the students in their second year PU, so I will try to avoid a lot of jargon, and I'll be very happy if there are questions towards the end of the lecture or even in the middle. If there are questions, I'll try to answer. this question. Okay, so let's get started with the topic. So the topics what I will try to cover today is a very basic question: what is quantum mechanics and what do we mean by quantum mechanics nowadays, and why quantum effects are not so obvious in everyday life. So, for example, you can ask this question: why quantum physics or quantum mechanics is not taught in the school level? And I'll try to explain some of these concepts. And one point what I want to motivate specifically for the students: why should you learn this subject, quantum mechanics? And very basic concepts and mathematics, which I will try to introduce, not at great details, because once you do a formal course in quantum mechanics, maybe next year in your career or so on, so then you will be introduced to this mathematics in great detail. And then, as I promised, I will try to give some very limited applications and make the platform what are going on in the present day. And if time permits, I will try to give maybe one or two slides about the results what are coming out from my own laboratory in Bangalore. This is in Raman Research Institute. So if people are interested, I'll be very happy to host visits and so on. Okay, so getting started, what is quantum mechanics? Quantum, just in the context of the English language or any other language, so this means the smallest amount of unit of something. For example, in context of energy, so this is called quantum of energy. So that means nothing can be smaller than this unit. For example, just to give the context, if you say money, then the quantum of money will be like 1 rupee coin nowadays. So then you can build up on this. Similarly, if you consider light, in that case, the light rays or the radiation what is coming out of your light emitting devices, be it LEDs or torches or even lasers. So you can say this quantum of light which comes out, they are called photons. Okay, so some of you or most of you must have heard about this term photons, which is quantum of light. So the discipline of physics, which is studying the smallest building block of energies, this is called quantum mechanics. So this is just to put the context. And how small is this and so on, we'll discuss. So this is where the second question comes into picture: why quantum effects are not seen on everyday life? For example, most of the everyday objects are pretty large size. Even bacteria and viruses are also pretty big compared to the quantum scale. And so we see collective effects of all these quantum of light or quantum of matter rather than what these individual quantum units are showing. So that is why we end up having to see an average effect instead of the pure quantum mechanical display, which typically is studied in the context of quantum mechanics. Another point is that most of the everyday experience is at high temperature. Even if you consider room temperature, this is, as you know, in Kelvin scale, this is close to 300 Kelvin, and which is very, very high compared to the energy unit in context of temperature, which is typically in the micro Kelvin or nano Kelvin range, where the quantum effects are important. So here also some averaging of the quantum effect goes on. So we end up seeing some average effect or classical effect. Then, most of these quantum effects, in order to see, for example, light in quanta, for example, one photon falling on a detector, our eye is also a detector, but we are not able to individually distinguish between one photon from another photon. So that is why we need high sensitive and sophisticated devices which can detect those single photons or single atoms, which are the units of quantum. If you don't have this kind of devices, which normally is difficult to procure outside sophisticated laboratory, then the effects which are seen are not really quantum. And then another thing which actually prevents easy conceptualization and many myths are spoken about quantum mechanics is that there is complex mathematics and conceptual understanding which typically prevents some easy conceptualization. So in today's lecture, I will try to give some very basic ideas so as to understand what is the basic way of understanding what is going on in the quantum world. So now coming to the next question, why should you learn quantum mechanics? So one of the idea, as I was telling just at the beginning of this lecture, today's Nobel Prize was also awarded to understanding the basic building block of light, and in that context attosecond pulses, very short pulses of light, and how these pulses of light actually interacts with the matter. So as you can see that not just today's example but most of the modern branches of science and technology development, physics, astronomy, even chemistry, medicine, electronics, for example the mobile phone which you are holding in your hand, its processors, the fundamental building blocks all obey the quantum mechanics. And in order to make progress in this direction, we need to know quantum mechanics for the technology development. So this is very obvious. Then from the philosophical point of view, quantum mechanics answer some of the deepest questions about the origin of the universe and how everything what we see around behaves and so on. So this is a good questions to ponder over. So then of recent interest, let's say past few years, maybe between last 5 to 10 years, all over the world, there is a huge focus also from the political perspective to develop so-called quantum technologies like quantum computers and then quantum secured algorithm, for example, banking sectors, etc., for security based on quantum mechanics. So these things actually are going to be implemented, and as of now most of these things are being implemented. So there is a huge interest to develop technologies for security, not just banking but also in defense, etc., and for computation based on the quantum mechanics. So another point is that there is a lot of nice aesthetic aspects of the quantum mechanics. So I hope that with these four not so complex motivational quotes, I could say that why should one be interested about quantum mechanics. So now some of the basic concepts. For example, there is this concept of photon, which I already have introduced. I will go a little bit deeper to explain where this concept of photon had actually come from. And this is mainly thanks to Albert Einstein and his discovery of photoelectric effect many years ago. And then there is a certain concept of fundamental uncertainty in any measurement. And then there is this statistical concept of probability and distribution function, which is built in the quantum mechanics. And then there are concepts of so-called superposition and entanglement. All of these words, specifically students have heard many times, but I will try to say what is going on here. Then there is a modified notion of the statistical physics. For example, most of the statistics and statistical physics which is taught in the undergraduate level is based on Maxwell-Boltzmann statistics. But at quantum regime, so there are two different types of statistics. One is called Bose-Einstein statistics, another is called Fermi-Dirac statistics. And this is depending on how you count the particles obeying certain statistics. And that also depends on the spin of the particle. So I will talk a little bit about this. And then the basic mathematics required for the quantum mechanics to understand is calculus and differential equation. So this is the background. So now coming to more realistic concept of photon. For example, many of you might be aware that Einstein have been awarded Nobel Prize for nothing else but his discovery for the law of photoelectric effect. So what was this? It was observed that if light falls on some metal, then there is electron ejected out of the metal. So as if light or the photons causing the electrons to emit. So now Einstein asked this question, what is special about it? Because normally, even if you say that you have some bowl with water and you throw stones, some water will spill out of the bowl. So what is so special about it? Because of some observation. Observation was that you expect that if the intensity of the light will be more, then more number of electron will come out. This is natural, right? You vigorously shake the bowl and then more water will come out. Similarly, electrons would also come out like that. But then what was actually observed is that the color of light is actually what is important. For example, if the light carrying photons are having higher energy, or they are having a wavelength which is shorter, then the energy of the electrons are higher. So this is a bit of a counterintuitive observation, and Einstein tried to give the explanation for that. And the experiment was the following. Suppose you have two capacitor plates, and monochromatic light whose frequency you could change is falling on one of the plate, and those electrons which are coming out, if you apply a negative voltage on the opposite electrode, and then you can see that only if you apply some finite voltage on this negative electrode, then this can be stopped. Otherwise, if you apply some positive voltage, then you can actually increase this photoelectric current. That means more electrons are coming out of it. So then what is going on? So then the experiment was not very difficult. You can find the energy of the electrons, or kinetic energy, which is proportional to the charge of the electrons times the voltage which is applied. And then you can actually see, by making the experiment very precise, that this V0, or the voltage where this current becomes zero, is actually proportional to some frequency difference with respect to a f0, which is previously measured for this particular metal, and then with a constant which is a ratio between two fundamental constants. One is h, which is known as Planck's constant. The value is given here, 6.626 into 10 to the power minus 34, divided by electron charge. And then, as if you have these energies which are coming out in packets, and these packets of energy, for example, the smallest unit is called photons, and then this is integral multiple of the smallest unit, and this was a surprise, and this is surprise number one. And the surprise number two was another effect called Compton scattering, which also proves the quantum nature of the light. If you have an electron which can be kept at rest experimentally, and if a photon with certain wavelength is coming and falling on that electron, then you can see, first of all, the electron can get a recoil momentum, and that momentum is actually obtained from the photon itself. And if the electron goes in one direction, then the scattered photon will go in another direction and with a different wavelength. So that means its color changed. The change in color can actually be experimentally measured, having this relationship against Planck's constant h divided by mass of the electron, velocity of the light, times 1 minus cos theta. Theta is the scattering angle with respect to the original photon. And from this, it shows that these photons exchange energy with electron. Then the photon energy decreases with collision with the electron, because here you can see the initial photon momentum and final photon momentum, they are different. Their wavelength is different, means momentum is also different. And then all these observations which came first, they prove that light comes in discrete packets of energy, and it is essential to provide a quantum description of the physical world. And Einstein gave exactly that. He put all this observation in context, and then the Nobel Prize was awarded. So now what is generally the quantum description of the physical world? Usually, if you take a ball and if a football player or is hitting the ball, if you take a picture, you have no difficulty in understanding that the position of the ball at the time of taking the picture will be very, very well defined. But this is for macroscopic object at high temperature. But if you see quantum mechanically, there is always a probability at any given time also to finding this ball somewhere in the space, not just as a very, very specific point. And that uh, comes with associated with the concept of probability. So the probability of finding the ball here, this is not 1 in quantum mechanics, this is less than 1. There is also probability of finding the ball elsewhere. So there is a distribution of probability as a function of distance where the ball can be found. So this probability distribution is typically depicted pictorially like this, and this distribution is also known as density distribution of this particle, and typically this is shown as something called modulus of psi square. So where the psi is known as wave function, this quantity Greek letter, and the wave function has no physical meaning, but its modulus square has a physical meaning. That is, what is the probability of finding the ball or the photon or the electron at any given position, which is d distance away from the coordinate system. So that is how these concepts are introduced. All right. So now how this probability distribution can be calculated. So as even from classical mechanics, you know that the total energy of the system is sum of its kinetic energy and potential energy. In quantum mechanics, the kinetic energy is written as minus h bar square by 2 into mass of the particle. If it is electron, then mass of the electron. And then this ddx, the first derivative, and its square operating on the wave function. This is the understanding of the kinetic energy. And the potential energy is a given potential, which is potential as a function of space acting on the wave function. So this is at the left hand side, and the right hand side gives you the so-called energy eigenvalue of the problem. And then that is how the so-called Schrodinger equation is introduced. So this is how the basic mathematics can be found for any given potential. This kind of equation can be solved. This is the differential equation solution problem for most of the potential, unless it's very complex for mathematically handling. So psi of r can be found, and so will the probability distribution at any given instant of time. So this is known as the Schrodinger equation. All right. So one example is something what in the beginning days of quantum mechanics is taught, is that what is the wave function or the probability distribution? It's mod square. If I have two classically forbidden regimes, left side and right side, where potential is positive infinity, and in between the 0 and L, so what would be the solution of the previous equation? This one, because this V of R now is known, and then as you can solve this problem, you can find the energies are discrete, so they are not continuous. So very many of the energy levels can be found. So these are E1, E2, E3, E4, and so on, and they are proportional to higher energy states like this quantum or this number n is square, and then this Planck's constant divided by 2 pi, which is h bar square, pi square, divided by 2 times mass times the length of this box. Okay, so these things, though they look simple, but modern day experiments can actually detect this kind of discrete energy levels in particles put in the boxes and so on. So now we will slowly get into the applications of this kind of situation, because here the application is, for example, the particle here is allowed to only move inside these two barriers. And the particular example what we are going to discuss now is also linked to that, which will be clear very soon. So the example is the laser, which almost on an everyday basis everyone encounters. So this is the full form is light amplification by stimulated emission of radiation. So what is going on here? So first of all, the invention of laser is one of the most significant developments in science and engineering over the past 60 years now. And as you can see that continuously every year there is a lot of progress in this direction. So in a sense, the full form is that first of all there is light or the photons, and they are being amplified, and there is a particular process which is the stimulated emission and this radiation which is of importance here. So I'll just uh, say what is going on. Suppose, for example, you have matter, and matter can be composed of atoms. So at present, let us take a very simple system of an atom which has two specific energy levels. Imagine that there are no other energy levels. So this is very similar to a situation what I just explained here, that you have multiple energy levels here, and we are considering a situation where only energy level E1 and E2 they are of consideration. All other energy levels are neglected. So this can be done in a specific example. So if this atom can go from one state from E2 to E1 and E1 to E2, and their separation is exactly same as the light photons which are coming and falling on this. The photons has an energy by now. I established this fact. So if this happens, then this atom will absorb this photon and go to the excited state. Now, once it goes to excited state, it has to de-excite at some point. So Einstein showed that the primary way of doing this emission is spontaneous emission. So that means spontaneously the atom will get de-excited from E2 going back to the most stable state, which is the ground state, and one photon will come out with exactly the same energy of the photon which absorbed. So this is the spontaneous emission. Another process is known as stimulated emission, and which is the main process for understanding the operation of laser. So what is happening in case of stimulated? So there are not one atom but many atoms, and now most of these atoms are in the ground state at a given time, and only very few in this picture I have shown one which is in the excited state. But imagine that somehow I can invert this population. Suppose at any given instance of time, I can put most of the atom or all of them in the excited state, and uh, uh, then we can. So there is a comment that my voice is not clear. Can someone tell if it is okay? Hello.
Hello, sir.
Yes, can you hear me? Because there was a comment saying that the voice is not clear. Is it
But
okay?
PPT is not visible, sir.
Sorry? No, I just saw a message saying that the voice is not clear. So
Professor, voice is clear. We can.
voice is clear. Okay, fine. Okay, then I will continue with the presentation. Can you hear and
Yes, sir. Yes,
see?
sir.
Okay, okay. All right. So maybe the person who wrote can increase the volume of the computer. So, so as I was continuing with the uh, presentation, so if you can invert the population by pumping energy to the system, then most of the atom will be in the excited state. Now, if one of these atoms spontaneously decays, so there will be one photon coming out. This photon can stimulate ejection of another photon from the excited state. So as you can see, if you can read this picture from left and right, so one photon coming out, then it can make sure that two photon comes out from the next atom, then three, and so on. So at the end, a large number of photons all are in the same phase, all are in the same direction, all are having same frequency. will come out. So this kind of pulsed output is what is via the stimulated emission. You have an intense light source with all same phase photons, and this kind of emission is known as laser. Okay, so one example is that suppose all the atoms are in the excited state. So once one spontaneous emission happened, this can cause the stimulated emission of a large number of photons, and these photons what we know as coherent output, and so this is why this is called laser, coherent laser source. Okay, so so this is a very simple way of explaining what is happening. So as you can see, in case of spontaneous emission, the excited atoms normally emit light, but simulated emission, the atoms in the state of population inversion, that means most of the atoms are in the excited state, they produce stimulated emission when the stimulated emission is by even a single incident photon can create a large intensity of light. So these photons which come out from spontaneous emission, I'll give an example. For example, in a normal light bulb, so they are all uncorrelated, incoherent, and they are going in all direction. In case of lasers, so they are all in the same direction. They are all having coherent, that means their phases are all same and they add up. So you get a very large intensity, very short pulses of light, and you can even make it continuous wave laser as well. So for example, this is in the laboratory, you can see a very well directed single frequency laser output coming out of such a laser boxes. So what is happening here? So all I wanted to say, so there is a medium. First of all, the medium, you have to prepare these atoms all in the population inverted state. So that is done by pumping the medium by some thermal source or by some additional light source as well. And then from one direction, if you shine some dim light, then a very bright light will come out from the other direction. So in a sense, what is happening? So you need three main components. One is an active medium. So this consists of collection of atoms. It can be molecules or ions. They can be in solid, liquid, or gaseous form. And then this medium is actually amplifying this light wave coherently. So this medium has to be kept in the population inverter. Then there is an optical resonator. So that means two mirrors which are actually causing the output energy to be coming out of the laser. I will give another slide on that. And then there needs to be a pumping source. Okay. So then, so this resonator is typically shown by two mirrors. One is a 100% reflecting mirror. Another is a semi-transparent mirror. So that means some light can come out of this mirror, and other mirror, no light can come to the left side, and these photons inside the medium will be reflecting back and forth unless one or two will come out from the one side. So what is happening is that you have all these atoms inside this active medium, and which is pumped by some other source, and there are always some ground state atom and a lot of excited state atom, and then there is a totally reflecting so-called rear mirror, and then there is a partially reflecting output mirror, and the laser output comes out of this partially reflecting output mirror. And then this output is actually the coherent laser, which is the main. So first of all, as I was saying, this is monochromatic because all photons are having same energy. So they are having same frequency or same wavelength. So single color. Then they are coherent. So all the light waves of individual photons, so they are all in phase. And then they are also like in a beam. So non-divergent. They have a very nice directionality. So these three are the main properties of the lasers. So they are not having divergence, they are coherent and monochrome. Okay. So now there are many types of the lasers. So for example, if you use active medium like gas, helium neon atom, carbon dioxide molecules, argon atom, ion, krypton atom, ion. So these things are typically pumped by electricity, pulsing electrical current. Then there are solid state lasers. For example, one of the first laser was a ruby crystal. Nowadays, you can see ND-AG lasers or dye sapphire laser, even diode laser. They are very, very popular. And then they are pumped by either electricity or by light, depending on the property. Then there are lasers even in the liquid state. So you can use dyes in water and then they are pumped by light. So that's how this laser. For example, ruby laser was the first type of laser and this was first demonstrated in 1960, more than 60 years ago now by Professor Maiman. And then in that case, so this consists of aluminum oxide and then some of the aluminum atoms are replaced by chromium, and what happens is that you can go from ground state, excite using some green pumping light, and then go to some intermediate excited state, which will fast decay into something called a metastable level. And all this aluminum oxide eventually, which especially this chromium doped part, so they will go to the metastable excited state, and then once one single photon at this wavelength come, this spontaneous emission or cascaded radiation will start, and you will start to see this strong red emission at 692.7 or 694.3 nanometer, and this is a laser output. And this is the first ruby laser where they used 100% reflecting mirror in one side and 95% reflecting mirror in the other side, and then the power supply is actually given to pump the ruby crystal, and then the strong laser output is used for the application. Okay, so just to give a number, so few megawatts of power can be emitted in few tens of microsecond. And now, as you can see, so this was in the initial days. Now people have gone down to attosecond, and they have also increased the output power from megawatts to terawatts level. So it's very high power for very short pulse duration, and this gives rise to the exciting quantum observations in the modern day. Okay, so similarly, the active medium can be used as a helium neon laser. The principle is very similar, and then they are also red light at the helium neon output 632 nanometer can be used for the laser output. So this one 632.8 nanometer laser output can be seen, and as you can see, this is an actual picture of the laser output coming from this laser oscillator box here, and a lot of laboratories nowadays will have this kind of lasers for many experiments and so on. So similarly for semiconductor laser, people typically take into account N-type doping and P-type doping, and the refractive index variation between the two sides of N and P is giving rise to an internal cavity, and the laser output is used from the semiconductor diode laser. And these type of lasers are most often used in supermarket for barcode scanner, etc. So they are in everyday life. Okay, so now many applications of laser, which is one of the fundamental or fast demonstration of quantum mechanical ideas. As many of you know, they are used for surgery, and then they had been used in CD players, etc. Then telecommunication, information systems, communication with satellites, and then creating hologram. So they are also used as weapons and radar systems, and then also glass and metal cutting industry, and of course in fundamental research in atomic and nuclear physics. And I have omitted a few because there is just too much of the application of the lasers in this kind of thing. Okay, so for example, what are some other applications of using the basic quantum mechanical ideas, which is the main reason for developing these lasers? I'm sticking a lot with the lasers, as you know, also a bit motivated by today's Nobel Prize, because that is really great tribute for so many years of research with lasers. And then one of the applications is precision spectroscopy, finding the corresponding transitions in different atoms very precisely. Then there is another idea where I will spend maybe 5 or 10 minutes what we do in our laboratory, laser cooling and trapping of neutral atoms and understanding the properties of the atoms and to utilize them for next generation devices. I will spend a few minutes there. And then also to provide intense heat in controlled fusion experiments, etc. And obviously using quantum computation and quantum communication. Definitely the lasers from one place to another is a fantastic communication tool. And but on top of that, using lasers to trap and cool and manipulate atoms actually paved the way for using these atoms as computers. So they are being used for quantum computation and quantum. So I will spend some time what is happening to do this laser cooling and trapping, and then if time permits, I will say something about this quantum advantage using this cold and trapped atoms. Okay, so in general, the idea is that if you have a laser, as you know, there will be single photons coming out of this laser, and these photons have a momentum, which is h bar k, and this uh, laser light can interact with an atom, which is moving towards the laser, and then if you can see, if the atom is moving, so it will have so-called Doppler shift depending on its velocity. If the laser light frequency is slightly less than the atomic transition frequency, then what may happen is that the due to the motion of the atom, it can actually see the light Doppler shifted and it can absorb this light. And once it absorbs this light, it has to emit in this nanosecond time scale, 10 nanosecond time scale. And now, once it absorbs the light, then it will have a decrease in the velocity. The decrease in the velocity is velocity minus h bar k momentum divided by mass. Okay, so now this reduces the velocity of the atom. Now, once this velocity of the atom is reduced, this spontaneous photon can be emitted in all direction, and this on many cycles will average out to be zero. So there will be an on an average the atom is slowed down. Once it slowed down, so that means in other words, from your concept of temperature, you can see that its temperature got reduced because the corresponding temperature of any atom or a bunch of atoms is the sum of their kinetic energies. If it slows down, then half mv square, its kinetic energy is also slowing down. So that way this leads to so-called cooling of the atom. Okay, so now if you can shine the laser light from left and right both direction, so the force on this atom in the velocity space will be a bit asymmetric, because as you can see, if the atom was moving with some velocity to the left, then it will predominantly absorb from the left laser. If it moves to the right, it will absorb from the right laser. So the total force has some kind of a profile, which is force is proportional to the velocity. So this is very similar to what happens for the friction or the dissipative medium. So force being proportional to velocity and minus of velocity, so this leads to a overall reduction of the velocity. So velocity dependent force actually gives rise to the damping of the system or the, so generalized idea of this is that you can shine light from all six direction, x, y, z, and its plus and minus side, and then you will have a region where you can see where all this laser light overlaps and there are atoms. So all these atoms are actually slowed down atoms or very cold, and I'll tell you what is this temperature. So this kind of things are known as optical molasses. Okay, so it's like the molasses, but only it's done with light. So that's why optical molasses. So proceeding with that, there is another associated concept of Zeeman effect. So in presence of a varying magnetic field in space, the energy levels of the atoms varies as a function of distance. and this variation causes also a special dependence on that force or the so-called scattering force, and this gives rise to both a damping force, as I explained before, and a specially dependent force, which is very similar to the Hooke's law here, and this gives rise to the magnetic trapping. So since it's the optical molasses plus magnetic trapping, so this is known as magneto-optical trapping of the atom. So this is normally created by current carrying loops, this varying magnetic field and laser light from all six directions, these big red arrows what I have drawn in that cartoon. And this is how the trapping and pulling simultaneously works as an answer. So typically you can collect uh, 10 to the power 9 to 10 to the power 10 atoms in such magneto-optical traps, and then the velocity of these atoms in these magneto-optical traps are very low, of the order of centimeter per second, whereas at room temperature the velocities are of the order of 30,000 centimeter per second or something like 300 kilometer per second. So from very high velocity, you can get down to very low velocity. So the kinetic energies are also very low. So you can go from room temperature to something like micro Kelvin temperature, as you can see here. Okay. And this is like a macroscopic size trap. So as you can see from our lab, you can actually see these atoms are in space. They are trapped in space inside a vacuum chamber, and the light which is coming out of these atoms, you can actually collect them in a CCD camera, and you can actually see what these atoms are doing individually and collectively. For example, we do a lot of this trapping. We trap not only means we trap sodium atoms, we trap potassium atoms, and we do research using this trap and ultra cold atoms at microkelvin temperature. So what kind of research we do? One example, not getting into too much detail. So if you have these atoms trapped in the space, and if you send a polarized light, and in presence of a magnetic field, there is a polarization rotation, which is known as Faraday rotation. So you can actually measure the Faraday rotation, how many degrees it rotated. And so if we did not know the magnitude of the magnetic field, we can actually, looking at the signal, infer what is the magnetic field very precisely. And this kind of measurement of magnetic field is also known as magnetometer. So we have been, discovering and demonstrating this magnet magnetic rotation sensor or magnetometry using this cold atom over the past 5 years or so. We can actually show that over a large range of magnetic field, looking at this kind of signal from this cold atom, we can actually measure very precisely this magnetic field with accuracy of 1 part in 10 to the power 15 or so. And then we can also not only show the magnetic field magnitude, but also by looking at the signal shape and size without getting into too much detail, show the direction of this magnetic field, or can use it as a vector magnetometer, or we can even see the time varying magnetic field. For example, one uh, use case is that our heart muscles contract and expand by electrical pulses, and these electrical pulses actually comes with this kind of time scale, and any electrical pulses will cause magnetic field outside our body, and that magnetic field can be measured very precisely using our magnetometers using the atoms. And for example, these trapped atoms can be used very precisely, what we call this spin noise spectroscopy signal, using these cold atoms trapped in space, and from the signal we can use it as a magnetometer. So I just wanted to highlight some of the modern research what we are doing using this trapped and cold atom to develop this kind of quantum sensors, and applying them for various detection techniques, which has many applications. So I will end the lecture here, and I'll be happy to take some questions at this stage.
Thank you very much, sir.
Thank you. So
So
I'll
any
be
questions?
happy to answer questions.
I request students to mention in the chat box if you have any queries, or you can raise your virtual hand so that we can unmute and you can directly ask the question to students. You can directly ask question and sir will be able to answer directly. They got any questions from YouTube channel? Any questions typed in the YouTube channel?
ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಯಾವ್ದೋ ಕ್ವಶನ್ಸ್ ಇಲ್ಲ ಸರ್ ಇಲ್ಲಿ ಹಾಕಿಲ್ಲ.
Not in the WebEx, it's in the YouTube. I am asking you. So as of now, there are no questions, sir.
Okay.
So if any questions, please do let us know through the WhatsApp group or email, or you can speak over a call and tell us about your queries or any questions so that we can share them with sir and get the answers, and we'll update you back. Sir, we request you to give few questions for the question bank publication for the students
Okay.
for CET purpose.
Sure. I'll do that. Yeah.
And meanwhile, we will be able to host a Nobel lecture series, sir.
Okay.
Down the line, after announcement of all chemistry, biology, and other domain peace and economics areas also. So for this physics area, we would like to invite you to deliver this session, sir.
Okay.
So we will share you the details very shortly. So it will be grateful if you agree for that and deliver the session on that Nobel Prize lecture series, sir.
Mm-hmm. Yeah.
Is that okay, sir?
Yes, fine. I'll be happy. Yeah.
Just a minute, sir. I will check with our CEO, Dr. M. Ramesh, sir. He would like to speak. Yes, sir. He is connected.
Good evening, Professor.
Namaskara. How are you?
Good. Again, it was a very informative and insightful talk.
Nice to meet you. Thank you very much.
Friends would have got a lot of take-home message from your talk. As my colleague Mr. Umesh told, we'll be hosting Nobel Lecture Series
Mm-hmm.
probably in the first week of November,
Okay.
7th onwards. We'll be inviting you for one of the talks on physics Nobel.
Okay.
So we will inform you very shortly after announcement of all the Nobel Prizes. So thank you very much, Professor.
Thank you.
So, sir, there are no questions in the chat box and YouTube channel also.
Okay.
So we'll wind up formally, sir.
Okay.
Shall
Thank
we
you.
wind up, sir?
Yes,
Ramesh, sir.
please go ahead. Yeah.
Okay. Thank you very much, Professor.
Thank you.
Grateful to you, friends.
Thank you very much, sir. On behalf of KST and on behalf of all the teachers and students fraternity, I once again thank you and grateful for accepting our invitation to deliver today's session. Thank you very much, sir. Also, I would like to thank our colleagues, technical team, non-technical team who are behind this. And last but not least, I would like to thank all the students who have joined with us in this WebEx as well as YouTube channel. And down the line, many students will be watching this session in YouTube channel. If any questions and any feedback you would like to give, you can always reach us by using the contact number, WhatsApp group, or email. Thank you. Thank you once again. Thank you, sir. We'll stay in touch, sir, regarding that Nobel lecture series. Thank you, sir.